The outer solar system stretches cold and dark, beyond the familiar warmth of the inner planets we know best from Earth. Out here, past the asteroid belt, past the giant bulk of Jupiter, the Sun appears as little more than a bright star in the distance. The journey to Saturn covers nearly 1.5 billion kilometers from the Sun, a distance so vast that light itself takes over an hour to cross it. This is where we find the most beautiful sight in our solar system, a planet wearing a crown of ice that catches the distant sunlight and glows. Saturn appears first as a point of light, pale yellow and steady, growing slowly larger as the distance closes across the void between worlds. The planet reveals itself gradually, a sphere of cloud bands and subtle color emerging from what had been merely a bright dot against the stars. Then the rings become visible, first as a thin line crossing the planet's disk, then opening into their true extent as perspective changes. I find myself struck, even after years of studying this world, by how the rings transform Saturn from merely a large planet into something unique. You are listening to The Drowsy Astronaut, and tonight we are spending time with Saturn and its remarkable, slowly vanishing rings together. This journey will explore what the rings look like now, what they are made of, and why they will not last forever in their current form. The story we are following spans millions of years of slow change, though we will take our time with each aspect along the way. If you are listening from somewhere around the world tonight, feel free to share where you are in the comments below. And if you enjoy these slow cosmic journeys, a like or subscribe genuinely helps us keep making them. But for now, just get comfortable, and whenever you're ready, we'll begin. The rings extend far beyond the planet itself, reaching outward for hundreds of thousands of kilometers in a disk of frozen material orbiting together. From a distance, they appear solid and continuous, like a phonograph record surrounding the pale sphere of the planet at their center. The color is predominantly white and cream, the color of water ice, catching sunlight and reflecting it back toward any observer present. Darker bands cross the bright expanses, hints of structure that become more complex the closer one looks at the ring system. The overall impression is one of delicate beauty, a structure that seems too thin and fragile to exist around such a massive world. Saturn itself is enormous, with a diameter of over 116,000 kilometers at its equator, large enough to contain Earth 700 times over. Yet the rings that surround this giant are remarkably thin, averaging only about 10 meters thick across most of their extent outward. This proportion is difficult to grasp at first, requiring comparison to make it real for understanding. If Saturn's rings were scaled down to a diameter of 1 kilometer, maintaining their proportions exactly through the reduction in size, the thickness would be less than a sheet of paper. A compact disk provides another comparison, thin and flat, but Saturn's rings are proportionally even thinner than that familiar object. This incredible flatness results from the physics of orbital motion, where particles that stray above or below the ring plane are gradually pulled back. The rings are a natural consequence of gravity and collision, shaped over time into the thinnest structure of their size anywhere. The extent of the rings from inner edge to outer edge spans approximately 280,000 kilometers of radial distance outward. This is roughly 3/4 of the distance from Earth to our moon, a substantial span of space filled with orbiting material. The rings would stretch almost from Earth to the Moon if laid out in a line across that familiar distance for comparison. Yet despite this enormous extent, the total amount of material is surprisingly modest when considered as a single mass combined together. If all the ring particles were gathered together and compressed into a solid body, the resulting moon would be only about 400 kilometers across. This is smaller than Saturn's mid-sized moon Mimas, which has a diameter of just under 400 kilometers itself, for reference. The rings appear substantial from a distance, but they are mostly empty space with scattered particles catching the light that reaches them. This sparseness is part of what makes them beautiful, allowing sunlight to filter through and illuminate individual particles across the visible expanse. The brightness of the rings varies considerably depending on which region of the ring system receives attention from an observer viewing them. The outermost main ring, called the A ring, is bright and reflects sunlight efficiently back toward any viewing location available. The middle ring, called the B ring, is even brighter, the densest and most opaque part of the entire ring structure overall. Moving inward, the C ring appears dimmer and more translucent, allowing the planet to show through in places where particles are sparse. These variations in brightness correspond to differences in particle density and size distribution throughout the different ring regions present. Where particles are crowded together, more sunlight is reflected, creating the bright bands visible from Earth through modest telescopes even at this distance. Where particles are sparse, less light returns, creating the darker gaps and divisions that give the rings their characteristic banded appearance. The interplay of bright and dark creates a pattern of concentric rings that astronomers have studied for over 400 years of observation. The color of the ring particles is predominantly white or cream, the natural color of water ice when illuminated by sunlight from above. This icy composition was suspected for many years and confirmed through spectroscopic observations that identified the chemical signature of frozen water present. Some regions of the rings show subtle reddish or brownish tints, where other materials have contaminated the pure ice over time, accumulating. These contaminants may include rocky dust, organic compounds, or material from the tiny moons that orbit within the ring system itself. The temperature of the ring particles is extremely cold, approximately -180 degrees Celsius, in the shadowed regions away from direct sunlight. On the sunlit side, temperatures rise somewhat, but remain far below the freezing point of water at all times throughout the orbit. The particles exist in a permanent deep freeze, water ice that has remained solid for as long as the rings have existed out here. This cold preservation keeps the ice from sublimating away, allowing the rings to maintain their brightness over astronomical timescales of millions of years. The appearance of the rings changes gradually as Saturn orbits the Sun, with the tilt of the ring plane varying over the planet's 29-year orbital period. When the rings are tilted at their maximum angle toward Earth, they appear wide and open, displaying their full extent to observers below. When Saturn reaches the points in its orbit where the ring plane aligns with Earth's line of sight, the rings appear edge-on and nearly invisible. This cycle repeats every 15 years or so. Observers on Earth watching Saturn over the coming years will see the rings appear to narrow and thin as this edge-on approach continues. By March of 2025, the rings will be essentially invisible from Earth, reduced to a thin line that even large telescopes struggle to detect. This is not because the rings are disappearing at that moment, but simply because we are viewing them from the side rather than from above. The rings will then appear to open again over the following years as Saturn continues its slow orbit around the Sun, away from alignment. The current viewing angle allows observers to see the rings at a moderate tilt, neither fully open nor edge-on at this particular time. Through a modest backyard telescope, Saturn appears as a small but clearly defined planet, with rings visible on either side of the central disk. The Cassini division, a dark gap between the bright A and B rings, can be seen with careful observation under good viewing conditions. This gap appears as a thin, dark line separating the outer ring from the brighter inner ring beneath it in telescopic views. The experience of seeing Saturn through a telescope for the first time stays with most observers who have had that opportunity available. The rings appear so crisp and distinct that they seem almost artificial, too perfect to be a natural structure existing in space. The planet floats in the eyepiece, surrounded by its delicate crown, a sight that connects the observer directly to the outer solar system, far beyond. This visual impact helps explain why Saturn has captivated human attention for as long as telescopes have existed to reveal it. The sunlight that illuminates the rings left the Sun about 80 minutes before reaching Saturn at its current distance from us. This is the same light that left our star when events were happening on Earth, 80 minutes in the past of any observation. The light reflects from the ice particles and begins its return journey toward Earth, taking another 80 minutes or so, depending on orbital positions. By the time we see the rings, we are viewing them as they appeared roughly 2.5 hours earlier in actual time. This time delay is a constant feature of observing the outer solar system, where distances are measured in light hours rather than light minutes. Saturn is never seen as it exists at this very moment, only as it existed when the light we receive today first left its vicinity. The rings we observe tonight were in their current configuration hours ago, continuing their slow orbit while the light traveled toward our instruments. This delay makes no practical difference for observation, but adds a layer of temporal distance to the spatial distance already separating us. The particles making up the rings orbit Saturn at different speeds depending on their distance from the planet's center of mass below. Inner particles orbit faster, completing their circuits in just hours, while outer particles move more slowly and take longer to complete their paths. This differential rotation means the rings are constantly churning, particles sliding past one another as they follow their individual orbits around Saturn. The rings are not a solid structure, but a flowing river of ice, each particle following its own gravitational path through space. The stability of this configuration has persisted for a long time, though perhaps not as long as astronomers once assumed it had endured. Recent evidence suggests the rings may be surprisingly young, perhaps only 100 million years old, rather than dating back to Saturn's formation. This would mean the rings appeared when dinosaurs still walked the Earth, a startling thought that places them in a different cosmic context. The evidence for this young age comes from measurements of ring mass and the rate at which the rings are losing material to Saturn below. The rings are slowly disappearing, draining into Saturn's atmosphere through processes we will explore as this journey continues forward. Ring rain, gravitational drag, and other mechanisms are stealing ice from the rings and depositing it into the planet below constantly. The rate of loss is substantial when measured over astronomical timescales, enough to completely drain the rings in perhaps 100 to 300 million years. We are fortunate to exist during the period when Saturn still wears its famous crown of ice for observation. The beauty visible today is temporary on cosmic timescales, a feature that will not last forever around this particular planet. Future observers, millions of years from now, may look at Saturn and see a ringless world resembling the other gas giants without prominent ring structures. The bright bands of ice that define Saturn in our telescopes will thin and fade over timescales far longer than human civilization, but short compared to planetary history. What we see tonight is not eternal, though it appears unchanged from year to year in any human lifetime of watching. For now, the rings remain, bright and beautiful against the darkness of the outer solar system, surrounding this remarkable world completely. The ice particles continue their endless orbits, reflecting sunlight back toward Earth with each rotation around the planet below them. The structure appears solid and permanent through any telescope, unchanging over the span of any single observation session conducted tonight. Only the accumulated measurements of decades reveal the slow changes that will eventually transform Saturn into something quite different from what we know. The rings that appear so solid from a distance are not continuous sheets of material at all when examined more closely from nearby. They are instead composed of countless individual particles, each one orbiting Saturn independently on its own gravitational path around the planet. These particles range enormously in size, from microscopic dust grains smaller than smoke particles to chunks of ice larger than houses standing. The ring system is a vast collection of frozen debris, not a single coherent structure despite its appearance from Earth below. The composition of these particles is overwhelmingly water ice, the same substance that forms snowflakes and glaciers here on Earth's surface. Spectroscopic analysis has confirmed this icy nature through observations that identify the chemical signature of frozen water across the rings entirely. The ice is remarkably pure in many regions, reflecting sunlight with a brightness that indicates minimal contamination by other materials mixed throughout. This purity is somewhat surprising given the age of the rings and their exposure to the dusty environment of space surrounding them. Small amounts of other materials are present within the ring particles, including rocky silicates and complex organic compounds called tholins appearing throughout. These contaminants give some ring regions their subtle reddish or brownish tints when viewed under careful observation from spacecraft visiting. The proportion of non-ice material varies throughout the ring system, with some areas appearing more contaminated than others do consistently. The overall composition remains dominated by water ice, which accounts for approximately 95% of the ring mass present. The size distribution of ring particles follows patterns that scientists have studied extensively through various observation methods over the years. The smallest particles are microscopic, dust-sized grains that scatter sunlight in distinctive ways detectable from distant observing platforms and spacecraft present. Medium-sized particles, from centimeters to meters across, comprise the bulk of the ring mass distributed throughout the system overall. The largest particles, reaching sizes of 10 meters or more, are relatively rare but contribute significantly to the total mass contained within. Most of the particles that would be encountered traveling through the rings fall in the range between 1 centimeter and 10 meters diameter. These chunks of ice are small enough to be numerous, yet large enough to reflect substantial amounts of sunlight back toward observers viewing them. A typical ring particle might be the size of a snowball, an ice cube, a basketball, or a small car depending on location within the ring system. The variety in size creates the complex optical properties that give the rings their distinctive appearance under different lighting conditions. The physical structure of individual ring particles is not simple solid ice, like an ice cube from a freezer would be for comparison. Instead, the particles are porous and somewhat fluffy, more like loosely packed snowballs than dense ice chunks in character. This porosity results from the gentle collisions that have shaped the particles over millions of years of orbital interaction within the ring system. The particles are fragile by earthly standards and would crumble easily if handled, though of course no human hand has ever touched them. The surface of a typical ring particle would be covered in a layer of frost, ice crystals that have accumulated over countless years of existence in space. This frost coating helps give the particles their high reflectivity, scattering sunlight efficiently in all directions from irregular surfaces present. The texture would be rough and irregular, shaped by countless small impacts and the slow growth of ice crystals in the vacuum of space. A close look would reveal a surface like fresh snow, white and crystalline, ancient yet constantly renewed by sublimation and condensation. The particles are separated from one another by distances typically larger than the particles themselves, on average throughout the rings. The rings are mostly empty space, with ice chunks scattered through that space at densities that vary from region to region across the system. Even in the densest parts of the B ring, the spacing between particles averages several meters, at minimum typically. An observer floating within the rings would see ice chunks in all directions, but would also see the darkness of space between them clearly. The motion of the particles creates a constant slow churning as inner particles overtake outer ones in their faster orbits around Saturn. This differential motion leads to gentle collisions between particles as they pass one another in their slightly different orbital paths overhead. The collisions are low-velocity encounters, more like bumping than crashing, because neighboring particles move at nearly the same speeds regardless. These gentle impacts are what keep the rings so thin, damping out any vertical motion and confining particles to the ring plane. When two particles collide, they typically bounce apart, with some exchange of material and momentum occurring during the brief contact. The collision may chip small fragments from one or both particles, adding fine dust to the ring environment surrounding the impact location. Some collisions result in temporary sticking, with particles clinging together briefly before separating again on subsequent orbital passes by each other. The constant, gentle jostling shapes the particles over time, rounding sharp edges and mixing surface materials between neighboring chunks throughout the system. The temperature of ring particles depends on whether they are in sunlight or shadow at any given moment during their orbit. Sunlit particles warm to approximately minus 160 degrees Celsius, still extremely cold, but warmer than the shadowed side reaches. Particles in Saturn's shadow cool further, dropping to minus 200 degrees Celsius or below in the darkness away from illumination. This constant thermal cycling, warming and cooling every few hours, may contribute to the structural evolution of particles over time through thermal stress. The orbital period of ring particles varies with distance from Saturn, following the same gravitational laws that govern all orbiting objects everywhere. Particles at the inner edge of the main rings complete one orbit in approximately 5 hours of continuous motion around the planet. Particles at the outer edge of the A-ring take closer to 14 hours to complete the same orbital circuit around Saturn below. This difference in orbital period is what causes the constant sliding motion between neighboring regions of the ring system perpetually. The speed of ring particles relative to Saturn is substantial, thousands of meters per second, though particles near each other move at nearly identical velocities relative to one another. This high orbital velocity is necessary to balance Saturn's gravitational pull and maintain stable circular orbits at each distance from the planet. The particles are in free fall, continuously falling towards Saturn, but moving sideways fast enough to continuously miss it in their paths. This balance of gravity and motion keeps the rings in place, neither falling into the planet nor flying away into space. The collective mass of all ring particles has been measured through its gravitational effect on spacecraft passing nearby during missions to the Saturn system. The Cassini spacecraft, which orbited Saturn for 13 years, provided the most precise measurements of ring mass during its close approaches to the planet. The total mass of the rings is approximately 15 quadrillion kilograms, which sounds enormous, but is actually quite modest for such an extensive structure extending so far. This mass equals only about 40% of Saturn's small moon Mimas, a comparison that illustrates the ring's relative insubstantiality overall. If all the ring particles were somehow gathered together and compressed into a single solid body, the resulting moon would be disappointingly small to most observers. This hypothetical moon would measure only about 400 kilometers in diameter, smaller than several of Saturn's existing moons already present nearby. The rings appear vast and substantial, but their total material content is modest, spread thin across their enormous extent around the planet. This modest mass is part of why the rings are vulnerable to loss processes that are slowly draining them away over time. The individual ring particles know nothing of their collective beauty or their slow collective disappearance over the ages, continuing around Saturn. Each particle simply orbits, following gravitational law, occasionally bumping against neighbors, gradually losing or gaining small amounts of mass through impacts. The rings emerge from this simple behavior repeated countless times across billions of individual particles, moving together in patterns created by physics alone. The complexity and beauty we observe arise from simple rules applied at enormous scale throughout the ring system. The brightness of the ring system results from all these individual particles reflecting sunlight back toward Earth and other observing locations simultaneously. Each particle contributes its small share of reflected light, and the sum of billions of contributions creates the visible rings we observe from our distance away. Where particles are dense, more light returns, creating bright regions visible even from Earth through small telescopes aimed at Saturn. Where particles are sparse, less light returns, creating the dark gaps and divisions that pattern the ring system's appearance distinctively. The particles have existed in their current configuration for perhaps 100 million years if recent estimates of ring age prove accurate with further study. Before that, they may have been part of a moon or comet that ventured too close to Saturn and was torn apart by tidal forces operating. The ice that makes up the particles has existed far longer, formed in the outer solar system when the planets were still young, billions of years ago. The material is ancient, even if its current arrangement as a ring system is surprisingly recent in cosmic terms. The particles will not exist in this configuration forever, as processes are slowly removing material from the rings and depositing it into Saturn below. Some particles fall directly into the atmosphere, captured by drag or magnetic effects that we will explore as this journey continues forward. Other particles are swept up by moons or broken into dust that drifts away from the ring system over long timescales of millions of years. The particles we observe tonight are temporary residents of the ring system, passing through on their way to eventual destruction elsewhere. The beauty of the rings lies partly in this impermanence, this temporary gathering of ancient ice into a structure that will not last forever around Saturn. We see the rings at this moment in their existence, neither at their beginning nor at their end, but somewhere in between those bookends. The particles orbit on, indifferent to observation, following physics without intention, creating beauty without awareness of doing so at all. They are simply ice, frozen water, orbiting a planet in patterns that happen to catch the light beautifully. The ring system, that appears as a single structure from Earth, resolves into distinct regions when observed more closely by spacecraft and powerful telescopes. These regions have been given letter names by astronomers, assigned in the order they were discovered, rather than by their position from the planet. The main rings carry the designations A, B, and C, with additional fainter rings named D, E, F, and G, extending the alphabet further outward and inward. This naming convention can be confusing at first, but the letters have become standard references for discussing different parts of the ring system. The D ring is the innermost of Saturn's rings, extending from just above the cloud tops to the inner edge of the brighter C ring beyond it. This region is extremely faint, barely visible even to spacecraft cameras passing nearby, containing only sparse material distributed thinly across its extent. The D-ring particles orbit very close to Saturn, completing their circuits in just 5 to 6 hours at the highest orbital speeds in the entire ring system. This inner position makes the D-ring vulnerable to atmospheric drag and other processes that are slowly pulling material into the planet below. The C ring, sometimes called the crepe ring for its translucent appearance, extends from the outer edge of the D ring to the inner boundary of the dense B ring. This region appears grayish and semi-transparent, allowing the planet's disk to be visible through it under certain lighting conditions during observations. The particles here are less densely packed than in the brighter rings beyond, creating the characteristic dimness that distinguishes this region from its neighbors. The C ring contains several narrow gaps and ringlets that add structure to its otherwise uniform dimness throughout its extent. The boundary between the C ring and the B ring marks a dramatic change in the character of the ring system visible to any observer. Crossing this boundary, the sparse scattering of particles gives way to the densest concentration of material anywhere in the rings around Saturn. The B ring is the brightest and most opaque part of Saturn's ring system, reflecting more sunlight than any other region of comparable size in the structure. This ring contains perhaps 2/3 of the total ring mass, making it the dominant component of the entire system surrounding the planet. The B ring extends for about 25,000 kilometers in radial width, a substantial portion of the total ring system extent from inner to outer edges. Within this region, particle density is high enough that the rings become effectively opaque, blocking the view of stars behind them during occultation observations. The color here is the purest white found anywhere in the rings, indicating clean water ice with minimal contamination from other materials mixed in. The B ring's brightness and density make it the most visible part of the ring system from Earth. Through even modest telescopes aimed at Saturn, the outer edge of the B ring ends at a dark gap that is visible from Earth. Through small telescopes under good viewing conditions, favorable for observation. This gap, called the Cassini division, appears as a dark line separating the bright B ring from the A ring beyond it across the ring system. The division is named for Giovanni Cassini, the Italian astronomer who first observed it in 1675 through his telescope in Paris. For over 3 centuries, this gap has served as the most prominent landmark in Saturn's ring system for observers viewing from Earth's surface. The Cassini division is approximately 4,800 kilometers wide, large enough to contain a small planet within its span across the rings. Despite appearing dark, the division is not completely empty, but contains sparse material similar to the faint inner rings in density and character. The particles here are less numerous and reflect less light, creating the dark appearance that makes the division stand out against the bright rings beside it. The emptiness is relative, not absolute, a thinning rather than a complete absence of ring material within this prominent gap. Beyond the Cassini division lies the A ring, the outermost of the main ring components that are easily visible from Earth through telescopes. The A ring is bright, but noticeably less opaque than the B ring, with a density that falls between the dense inner ring and the sparse outer regions. The width of the A ring is approximately 15,000 kilometers, extending to the outer boundary where the main ring system effectively ends today. Within the A ring, several narrower gaps and divisions add additional structure to the already complex ring system, visible to observers. The Encke gap is a prominent feature within the A ring, a dark lane approximately 325 kilometers wide that circles the planet completely. This gap is maintained by the tiny moon Pan, which orbits within the gap and clears particles from its path through gravitational influence. The Keeler gap is narrower still, only about 42 kilometers wide, maintained by the even smaller moon Daphnis, orbiting within its empty lane. These gaps reveal that the rings are not static, but shaped by gravitational forces from the moons that share their orbital space around Saturn. Beyond the A ring, the ring system becomes much fainter and more difficult to observe from Earth, or even from nearby spacecraft. The F ring is a narrow, braided structure just outside the A ring, confined by 2 small shepherd moons that keep it from spreading outward. This ring is only about 100 kilometers wide, remarkably narrow compared to the main rings, with a complex structure that changes over time visibly. The braids and kinks in the F ring result from the gravitational influence of its shepherd moons, disturbing the particles as they orbit. The G ring is even fainter, a tenuous band of material orbiting well outside the main ring system at a distance of approximately 170,000 kilometers from Saturn's center. This ring is so sparse that it is virtually invisible from Earth, detectable only through careful observations by spacecraft passing through the Saturn system on their missions. The material in the G-ring is continuously replenished by impacts on a small embedded moonlet that releases debris into the surrounding space regularly. Without this replenishment, the G-ring would disperse and vanish within perhaps a few thousand years of losing its source of material. The E-ring is the largest of Saturn's rings by extent, stretching from inside the orbit of Mimas to beyond the orbit of Titan across a vast span of space. This enormous ring is also the faintest, a diffuse cloud of microscopic ice particles that would be invisible without specialized observations designed to detect it. The E-ring is fed by the moon Enceladus, which sprays water ice from geysers at its south pole into the surrounding space, continuously during its orbit. The fresh ice from Enceladus replenishes the E-ring, which would otherwise disperse into the surrounding space within just years of losing its supply. Moving through the ring system from inner to outer edge reveals a gradual transition from dense to sparse, from bright to faint, from ancient to recently replenished material. The main rings, A, B, and C, contain the vast majority of the visible material and have existed in their current form for millions of years, potentially. The outer rings, F, G, and E, are more dynamic, shaped by ongoing processes and requiring continuous replenishment to maintain their presence at all. The ring system is not uniform, but varied. Each region, with its own character and its own story of formation and evolution. The transitions between rings are sometimes gradual, with density changing slowly over thousands of kilometers of radial distance from Saturn's center. In other places, the transitions are sharp, with dense regions giving way abruptly to empty gaps at well-defined boundaries, visible in images. These boundaries often mark the influence of moons, whose gravity creates resonances that clear particles from specific orbital distances around Saturn. The ring system is sculpted by these gravitational influences, shaped as much by the moons as by the planet itself over time. The colors of the different rings vary subtly, with some regions appearing slightly redder or browner than the predominantly white main rings throughout. The innermost regions tend to show more contamination, appearing darker and less reflective than the purer ice of the B ring beyond them. The A ring shows intermediate coloration, whiter than the inner rings, but not quite as pristine as the brightest parts of the B ring inside it. These color variations record the history of contamination, with different regions exposed to different amounts of dust and debris over time. The structure of the rings contains information about their history and the forces that have shaped them over millions of years of existence around Saturn. Scientists read this structure like a book, interpreting the gaps, waves, and density variations as records of gravitational interactions and collisions occurring throughout. Each feature tells a story, though not all the stories are fully understood, even after decades of careful study by researchers worldwide. The rings remain partly mysterious, their origins and evolution still subjects of active investigation and debate among planetary scientists today. The beauty of the named rings lies in their variety, the way each region offers something different to the observer, patient enough to look closely at them. The dense brightness of the B ring contrasts with the translucent grey of the C ring. The dark Cassini division sets off both brilliantly from observers' vantage points. The narrow braids of the F ring differ entirely from the broad expanses of the main rings inside it around Saturn. This variety, within a single ring system, makes Saturn endlessly fascinating to study and observe, over time continuing. The dark gaps and divisions that cross Saturn's rings are not merely absences of material, but active features maintained by gravitational forces operating continuously. These empty lanes reveal the presence of invisible sculptors, moons whose gravity reaches across thousands of kilometers to shape the ring system around them. The gaps appear dark because fewer particles orbit there, but the reason for this scarcity is dynamic rather than accidental in nature. Understanding the gaps means understanding how gravity works across the vast distances of the Saturn system to affect small particles. The Cassini division, the most prominent gap in the ring system, spans approximately 4,800 kilometers between the B and A rings around Saturn. This division appears dark through telescopes on Earth, a black stripe separating the bright inner ring from the less dense outer ring beyond it. The darkness suggests emptiness, and while the Cassini division does contain fewer particles than the adjacent rings, it is not completely vacant throughout. Sparse material orbits within the division, similar in density to Saturn's faintest rings. But the contrast with the bright neighboring rings makes it appear dark by comparison. The Cassini division exists because of gravitational resonance with Saturn's moon Mimas, which orbits much farther from the planet outside the ring system itself. Particles in the Cassini division orbit Saturn at a period that is exactly half of Mimas's orbital period, a relationship called a 2-to-1 resonance between them. This means that every time a particle in the division completes 2 orbits, Mimas completes exactly 1 orbit around the planet as well. This regular timing causes the gravitational influence of Mimas to accumulate, repeatedly tugging particles in the same direction with each encounter. The repeated gravitational tugs from Mimas push particles out of the Cassini division over time, gradually clearing this orbital zone of debris. Particles that drift into the division from neighboring rings receive the same treatment, nudged back out by the accumulated gravitational influence of the distant moon. The division is not a static feature carved once and left alone, but an actively maintained emptiness, requiring continuous gravitational work from Mimas to preserve. If Mimas somehow disappeared, the Cassini division would slowly fill in with particles drifting from the adjacent rings over millions of years. The physics of orbital resonance operates throughout the solar system. Wherever moons and rings or planets and asteroids share orbital spaces together, Jupiter's asteroid belt has gaps maintained by resonances with Jupiter itself, emptied zones where asteroids cannot stably orbit over long timescales at all. Saturn's rings display the same physics on a smaller scale, with multiple gaps and divisions marking resonances with various moons orbiting beyond the rings. The ring system is a laboratory for studying gravitational dynamics, with the results written in the gaps between bright bands of ice visible to us. Within the A-ring, smaller gaps provide examples of a different kind of gravitational sculpting by moons orbiting within the ring system itself. The Encke gap is approximately 325 kilometers wide, a dark lane that circles the entire A-ring completely around the planet. This gap appears empty in most images, a black stripe crossing the pale ice of the surrounding ring material on either side. The emptiness is maintained by a tiny moon named Pan, which orbits within the gap and gravitationally clears particles from its path continuously. Pan is only about 28 kilometers in diameter, a small object that would barely be visible as a speck in most images of the ring system. Yet this tiny moon has enough gravity to influence particles for hundreds of kilometers on either side of its orbit around Saturn. As Pan orbits, its gravity pushes nearby particles away, preventing them from entering the gap and accumulating there over time around the planet. The gap exists because Pan is there, a visible record of an invisible gravitational influence operating constantly throughout each orbit. The edges of the Encke gap are not smooth but scalloped and wavy, showing the direct influence of Pan's gravity on nearby ring particles. These waves form as Pan passes, its gravitational tug pulling particles toward it, and then releasing them as it moves on. The waves propagate outward from Pan's location, rippling through the ring material like the wake of a boat moving through water on Earth. Images from the Cassini spacecraft captured these waves in exquisite detail, revealing the dynamic interaction between moon and ring material frozen in time. The Keeler gap is even narrower than the Encke gap, only about 42 kilometers wide, maintained by the even smaller moon Daphnis orbiting within it. Daphnis is approximately 8 kilometers in diameter, barely large enough to be considered a moon at all by most definitions used today. Yet this tiny object maintains its own gap in the ring system, clearing particles from its orbital path through the same gravitational mechanism as larger Pan nearby. The waves created by Daphnis are proportionately smaller than Pan's waves, but equally dramatic when viewed in high-resolution spacecraft images. The presence of these gap-clearing moons was predicted before they were directly observed, based on the existence of the gaps themselves in the ring system. Scientists reasoned that such clean, narrow gaps must be maintained by something, and small moons were the most likely candidates to fill this role. When Voyager and later Cassini spacecraft imaged the gaps closely, they discovered the predicted moons exactly where gravitational theory said they should be located. This prediction and confirmation represents one of the successes of celestial mechanics applied to the Saturn system over the years. Other gaps in the rings lack obvious moon-clearing explanations and remain more mysterious in their origins, despite decades of study. The Maxwell gap in the C ring, for example, shows no clear resonance with any known moon that could explain its presence within the ring system. Some of these unexplained gaps may be maintained by very small moons, not yet discovered hidden within the ring material itself somehow. Others may result from more complex dynamics that scientists have not yet fully understood or modeled accurately enough to explain. The gaps serve as windows through the ring system, allowing starlight to pass without obstruction during occultation observations from spacecraft and Earth. When a star passes behind the rings, as seen from a spacecraft, its light is blocked by ring particles and transmitted through gaps in the pattern. By measuring how the starlight varies as it passes through different parts of the rings, scientists can determine particle density and size distribution throughout. The gaps provide reference points of zero density, calibrating these observations against known empty regions within the ring structure. The existence of gaps demonstrates that the rings are not static, but dynamically evolving features shaped by ongoing gravitational processes continuously over time. The moons that maintain the gaps are slowly spiraling inward or outward themselves, meaning the gaps may shift position over millions of years of continued interaction. The particles in the rings are constantly jostling, moving, being pushed and pulled by forces they cannot resist in their orbital paths. The ring system is in constant slow motion, appearing static only because human observation spans such a tiny fraction of geological timescales. The dark lanes between bright rings provide contrast that makes the entire ring system more visually dramatic than a uniform disk would be to observers. The interplay of light and shadow, full and empty, creates the banded appearance that makes Saturn's rings so distinctive among planetary features anywhere. Without the gaps, the rings would appear as a single bright band, far less interesting than the complex structure we actually observe when viewing the planet. The gaps contribute to the beauty, even as they reveal the physics that shapes this delicate system around Saturn. The forces that create gaps are related to the forces that are slowly destroying the rings over millions of years of continued operation. The gravitational influences that clear gaps can also push particles towards Saturn, contributing to the loss of ring material over time, increasing steadily. The moons that maintain gaps are sculpting a structure that is simultaneously being erased by other processes operating throughout the ring system. The rings exist in a balance between creation and destruction, shaped and depleted by the same fundamental forces of gravity and orbital mechanics, always. The gaps will outlast the dense rings they separate, remaining visible as the surrounding material thins and fades over millions of future years, eventually. When the rings have largely dispersed, the gaps may still be detectable as regions of particularly low particle density, compared to their even more depleted surroundings. The record of gravitational sculpting will persist, even as the material being sculpted disappears into Saturn's atmosphere below, over time continuing. The gaps are written in the ring structure now, and will be readable for as long as any ring material remains orbiting the planet. The rings that appear so permanent from Earth are actually losing material continuously to Saturn's atmosphere below them every moment. This process, called ring rain, transfers ice from the rings to the planet at a rate that will eventually drain the ring system entirely over time. The discovery of ring rain came through observations of Saturn's upper atmosphere, where unexpected patterns revealed the presence of water falling from above. This water could only have come from the icy rings, carried downward by processes that had not previously been suspected to operate at such significant rates. The first hints of ring rain came in the 1980s from infrared observations made using ground-based telescopes on Earth, pointed at Saturn. Scientists noticed that Saturn's upper atmosphere showed unusual chemical patterns in certain latitudes that corresponded to the ring locations overhead above them. These patterns suggested that water and other molecules were entering the atmosphere from above, rather than being generated internally within the planet itself. The rings, made almost entirely of water ice, were the obvious source for this atmospheric water enrichment observed from Earth's telescopes below. The mechanism of ring rain involves the interaction between ring particles and Saturn's powerful magnetic field, extending outward through the ring system. Sunlight and plasma interactions can strip electrons from ice molecules on ring particle surfaces, creating positively charged ions in the process continuously. These charged ions are then subject to electromagnetic forces that can pull them along magnetic field lines toward the planet's atmosphere below. The ions spiral down the field lines, eventually entering Saturn's upper atmosphere and depositing their water molecules there to accumulate over time. The Cassini spacecraft, which orbited Saturn from 2004 to 2017, provided direct measurements of the ring-rain rate occurring. During its final orbits, Cassini flew between the rings and the planet's atmosphere, directly sampling the material falling from the rings above it. The spacecraft detected water ice, organic molecules, and other ring materials raining down at rates far higher than earlier estimates had suggested were likely. These measurements transformed our understanding of how quickly the rings are losing mass to the planet below them continuously. The current estimates suggest that approximately 1,800 kilograms of ring material fall into Saturn's atmosphere every single second, on average. This rate is equivalent to filling an Olympic swimming pool with ice approximately every 30 minutes throughout the entire year, continuously. The volume of material lost is substantial, enough to significantly deplete the rings over timescales measured in millions rather than billions of years passing. The rings that appear permanent to human observers are draining away on timescales that are short by planetary standards of measurement. The ring rain does not fall uniformly across Saturn's atmosphere, but concentrates at specific latitudes determined by the geometry of the magnetic field connecting to the rings. The material enters the atmosphere in bands, creating the distinctive chemical patterns first observed from Earth in the 1980s initially. These bands correspond to where magnetic field lines from different parts of the ring system intersect the planet's upper atmosphere below the rings. The pattern provides a map of the magnetic connections between rings and planet, visible in atmospheric chemistry from observations. The particles that fall as ring rain are tiny, much smaller than the larger chunks of ice that make up most of the ring mass orbiting above. Only the smallest particles, microscopic dust and ice grains, are affected strongly enough by electromagnetic forces to be pulled out of orbit entirely. These small particles represent only a fraction of the total ring mass, but are lost at significant rates compared to their total abundance in the rings. The constant creation of small particles through collisions replenishes this population, providing a continuous supply of material for the ring rain process. The sunlit side of the rings experiences different ring rain conditions than the shadowed side passing through Saturn's own darkness. Solar radiation is a key driver of the ionization process that creates charged particles susceptible to magnetic capture and transport downward. The ring rain rate may vary over Saturn's 29-year orbital period as the ring's angle to the Sun changes through the seasons passing. Seasonal variations in ring rain have been suggested by some observations, but not yet definitively confirmed through long-term measurements taken over full seasons. The water deposited in Saturn's atmosphere by ring rain has detectable effects on atmospheric chemistry and dynamics observable from spacecraft and telescopes. The influx of oxygen-containing molecules affects the abundance of various compounds in the upper atmosphere above the cloud tops below. These chemical effects can in principle be monitored over time to track changes in ring rain rate occurring throughout the Saturn system over decades. Long-term monitoring of Saturn's atmosphere may reveal variations in the ring rain that provide information about ring dynamics, invisible to direct observation. The ring rain process operates in addition to other mechanisms that also remove material from the rings and deposit it onto the planet below. Gravitational drag from Saturn's extended upper atmosphere affects the innermost ring particles most strongly during their close orbital passes. Small particles in the D ring are especially vulnerable, orbiting so close to Saturn that atmospheric drag gradually steals their orbital energy continuously. These particles spiral slowly inward, eventually entering the atmosphere directly, rather than falling along magnetic field lines like ring rain proper. The combined effect of ring rain and gravitational drag removes material from the rings faster than any replenishment process can restore it over time. Unlike the E-ring, which is continuously fed by the geysers of Enceladus, the main rings have no known source of new material being added. The material that falls into Saturn is lost permanently from the ring system, never to return to its original orbital location around the planet. The rings are in a state of net loss, slowly but inevitably draining away into the giant planet below them month by month. The rate of material loss, measured by Cassini, was higher than many scientists had expected before the mission provided its data. Some earlier models had suggested ring rain might be a minor process, losing only small amounts of material over very long timescales of solar system history. The Cassini measurements revealed a much more aggressive process, one capable of depleting the rings entirely in less than 300 million years at current rates. This faster timeline suggests the rings are more ephemeral than their ancient appearance would suggest to most casual observers. The discovery of rapid ring loss has implications for understanding the age and origin of the rings themselves, orbiting Saturn today. If the rings were truly ancient, dating back 4.5 billion years to Saturn's formation, they should have already been depleted by ring rain ages ago. The fact that substantial rings still exist suggests either that they are much younger than the planet or that past conditions allowed slower loss rates. Both possibilities are subjects of ongoing scientific investigation and debate among researchers studying the Saturn system. The ring rain that falls tonight is the same ring rain that has been falling for millions of years and will continue falling for millions more years to come. The process is slow by human standards, imperceptible to any observer watching Saturn through a telescope over a lifetime of observation. Yet the accumulated effect over geological timescales is substantial, capable of removing a significant fraction of the ring mass over periods that are short by planetary standards. The rings are disappearing, drop by microscopic drop, falling continuously into Saturn below. The innermost parts of Saturn's ring system are most vulnerable to loss, orbiting so close to the planet that multiple draining processes operate simultaneously on the particles there. The D-ring, which extends from just above Saturn's cloud tops to the inner edge of the C-ring, is the most endangered region of all the ring structures. Particles here orbit at the highest velocities in the ring system, completing their circuits in just 5 to 6 hours each time around. This close proximity to Saturn makes the D-ring the front line of ring loss, where material is continuously being stripped away into the atmosphere below. The primary mechanism driving D-ring loss is drag from Saturn's extended upper atmosphere, which reaches up into the inner ring region continuously throughout each orbit. Particles passing through this tenuous gas experience friction that gradually steals their orbital energy over many thousands of orbital cycles completed. As particles lose energy, they spiral slowly inward, dropping into lower orbits that bring them closer to Saturn with each circuit around. Eventually, the particles enter the atmosphere completely and are vaporized, adding their mass to the giant planet permanently. The timescale for this inward spiral is long by human standards, but short by astronomical measures of planetary evolution and change. A typical D-ring particle might take thousands of years to spiral from the outer edge of the D-ring to atmospheric destruction waiting below. This seems slow until compared to the age of the solar system, which exceeds 4 billion years of existence since planetary formation occurred. The spiral time is less than a millionth of the solar system's age, rapid enough to completely drain the D-ring many times over since Saturn formed. The D-ring still exists today only because it is continuously replenished by material drifting inward from the C-ring beyond it outward. Particles from the outer edge of the D-ring are replaced by particles arriving from the inner edge of the C-ring through similar processes. This replenishment maintains the D-ring's current appearance, but it also means the C-ring is slowly being drained to feed its inner neighbor. The loss propagates outward through the ring system, each region supplying material to the region inside it, closer to Saturn. The inward drift of material is not limited to the innermost rings, but affects the entire ring system to varying degrees throughout. Particles throughout the rings experience subtle forces that cause slow inward migration over very long timescales of millions of years. Continuing, collisions between particles can transfer angular momentum, with some particles gaining energy and moving outward, while others lose energy and move inward. The net effect of countless such exchanges tends toward inward migration, gradually feeding material toward Saturn over time. The gravitational influence of Saturn's moons also contributes to the inward migration of ring material through resonance effects operating throughout the system. Moons exterior to the rings can gradually extract angular momentum from ring particles through gravitational interactions at specific orbital distances, creating patterns. This extraction causes particles to spiral slowly inward, adding to the loss driven by drag and collisional processes occurring simultaneously within the rings. The moons that create the beautiful gaps in the rings also contribute to the ring's ultimate disappearance over time. The rate of inward spiral has been measured by comparing images of the inner rings taken decades apart by different spacecraft visiting Saturn. The Voyager spacecraft imaged the D-ring in 1980 and 1981 during their brief flybys of the Saturn system then. Cassini imaged the same regions starting in 2004, allowing comparison of features over more than 20 years of elapsed time between observations. Changes in the position and structure of D-ring features confirmed that material is indeed spiraling inward at measurable rates today. The innermost D-ring features have shifted noticeably towards Saturn over the decades between Voyager and Cassini observations of the same locations. Narrow ringlets in the D-ring moved inward by hundreds of kilometers over this period, directly demonstrating the inward spiral process occurring continuously. This rate of movement, extrapolated over millions of years, is consistent with the complete loss of the D-ring material on timescales similar to ring rain estimates. The two major loss processes, ring rain and inward spiral, operate together to drain the rings from multiple directions simultaneously. The C-ring, which feeds the D-ring, is itself slowly being depleted as material drifts inward faster than it is replenished from the B-ring beyond it. The C-ring particles orbit at greater distances from Saturn and experience less atmospheric drag than the innermost ring particles do continuously. However, collisional and resonance effects still drive slow inward migration draining the C-ring over timescales measured in hundreds of millions of years passing. The C-ring will thin and fade as the ring system ages, becoming more sparse and translucent over geological time. The B-ring, the densest and most massive part of the ring system, is the main reservoir that supplies material to the inner rings over time. This ring contains perhaps 2/3 of the total ring mass, enough to sustain the inner rings for many millions of years of continued loss and replenishment. However, the B ring is also subject to the same loss processes, losing material at its inner edge and receiving less at its outer boundary from beyond. The B ring will eventually be depleted as well, though it will be the last major ring component to disappear entirely from view. The A ring, outermost of the main rings, receives little replenishment from beyond and is slowly draining inward to feed the rings inside it over time. Material at the outer edge of the A ring is lost to the F ring region and beyond, where it disperses into interplanetary space eventually. The A ring will thin from both edges, losing material outward to space and inward to the denser rings towards Saturn's location below. This thinning will accelerate as the ring mass decreases, making the remaining particles more vulnerable to loss processes operating. The timescales for complete ring loss vary depending on which processes are considered and what assumptions are made about future conditions continuing. Conservative estimates suggest the main rings might persist for 300 million years at current loss rates measured by spacecraft observations. More aggressive estimates, incorporating both ring rain and inward spiral losses together, suggest complete depletion might occur in as little as 100 million years from now. The true timescale lies somewhere in this range, likely closer to the middle of these estimates based on current understanding. The inner spiral of ring material is invisible to casual observation, far too slow to detect in any human lifetime of watching Saturn through telescopes. Only the patient comparison of spacecraft images decades apart reveals the motion occurring, the slow drain of ice toward the giant planet waiting below. The rings appear static because our observations span such a tiny fraction of the time required for visible change to accumulate within the ring system. On geological timescales, the rings are flowing inward like a slow-motion waterfall, draining inexorably into Saturn over millions of years. The rings of Saturn are disappearing, but the timescale of this loss is almost impossible for human minds to fully grasp in any intuitive sense. Current estimates suggest the rings will be largely gone in approximately 100 to 300 million years from now, based on measured loss rates. This range sounds impossibly long, far beyond any human planning horizon or historical perspective we possess currently. Yet, compared to the age of the solar system, this remaining time is surprisingly brief, a mere fraction of the time Saturn has already existed, orbiting the Sun. The solar system formed approximately 4.5 billion years ago from a collapsing cloud of gas and dust between the stars. Saturn coalesced from this material early in solar system history, taking its place as the second largest planet orbiting our Sun since that time. If the rings were as old as Saturn itself, they would have existed for over 4 billion years already before our observations of them began. A remaining lifetime of 1 to 300 million years would represent only 2 to 7% of the time the rings had already lasted through. This arithmetic suggests something important about the current state of the rings when considered carefully and fully. If the rings were truly ancient, they would be more than 90% depleted, nearing the very end of their existence right now as we observe them. We would be witnessing the final remnants of a once magnificent structure, the last traces before complete disappearance finally occurs around Saturn. This seems possible, but it raises the question of why we happen to exist at just this special moment in ring history today. The alternative explanation is that the rings are much younger than Saturn itself, having formed relatively recently in solar system history. Somehow, if the rings are only 100 million years old, as some evidence now suggests, then we are not witnessing their final decline at all. Instead, we are seeing a ring system in its prime, with most of its existence still ahead of it over the next 100 million years continuing. This interpretation removes the coincidence of our existence during the ring's final moments, making our observation less statistically improbable in timing. The question of ring age remains actively debated among planetary scientists, studying the Saturn system today using available data. Evidence for young rings comes from their brightness and purity, which suggest they have not been exposed to space dust for billions of years. Evidence against young rings comes from the difficulty of explaining how such a large structure could form so recently in solar system history. Both sides have reasonable arguments, and the true answer may require future observations or missions to definitively determine with confidence. Regardless of the ring's origin, their future is clear, based on measured loss rates and understood physical processes operating within the ring system now. The ring rain and inward spiral will continue, draining material from the rings and depositing it into Saturn below continuously over time. No known process adds material to the main rings at rates comparable to the loss, meaning the net effect is depletion continuing indefinitely forward. The rings will thin, fade, and eventually disappear entirely over the next few 100 million years of continued evolution around Saturn. The timeline of this disappearance can be imagined through comparison with other long timescales in Earth's history. For reference points, 100 million years ago, dinosaurs still dominated the Earth, and mammals were small creatures hiding from large predators then. 300 million years ago, the first reptiles were just appearing, and life had only recently colonized the land from ancient oceans below. The rings will disappear on timescales comparable to the evolution of major animal groups on Earth, long by any human standard, but measurable against geological time. Looking forward, in 100 million years, the rings will be noticeably thinner than they appear today, if loss rates continue unchanged throughout. The B ring will still be the brightest component, but its density will have decreased, making it more translucent than currently observed today. The Cassini division will appear wider as the rings flanking it shrink, and the A ring may have thinned significantly from its present extent around Saturn. These changes will be gradual, spread over millions of years, invisible to any individual observer, but clear in accumulated records. In 200 million years, the ring system may resemble the sparse, faint rings of Uranus or Neptune, more than the magnificent rings of Saturn today. The bright bands that define Saturn's appearance will have faded to ghostly shadows of their current glory when viewed from distant observations. The Cassini division may dominate the ring system, with the remaining material confined to narrow bands between widening gaps throughout. Saturn will still have rings, but they will be difficult to observe from Earth without specialized equipment and techniques applied carefully. In 300 million years, the rings may be essentially gone, reduced to a thin disk of dust, barely detectable around the planet's equator region. Saturn will appear ringless through any telescope, its famous feature having disappeared into the planet's atmosphere over the intervening millennia of continued loss. The moons that once shaped and shepherded the rings will still orbit, but the material they maintained will have vanished completely from the Saturn system. Future observers will see a Saturn very different from the planet we know today in our time. The beings who might observe this ringless Saturn are impossible to predict or imagine with any confidence at all today. If intelligent life still exists on Earth in 300 million years, it will likely be descended from present organisms, but utterly changed by that span of evolution continuing. If humanity has spread to other worlds, our descendants might observe Saturn from multiple vantage points throughout the solar system simultaneously. Or no observers might remain, the solar system continuing its slow changes without any conscious beings to notice or care about planetary features. We are fortunate to exist during the period when Saturn still wears its magnificent rings for our observation and wonder today. Whether the rings are ancient remnants or recent creations, we happen to live when they are substantial and beautiful around the planet. Future observers may look back at our images of Saturn with rings the way we look at artist impressions of ancient geological eras today. The rings will become historical, something that once was but is no longer, a feature of the past solar system no longer present. The awareness of ring impermanence adds poignancy to observations of Saturn made from Earth and from spacecraft visiting the outer solar system. The beauty we observe is temporary, a fleeting configuration of ice that will not last forever around this particular planet in the future. This impermanence does not diminish the beauty, but perhaps enhances it, making each observation a moment captured from a passing phenomenon occurring around Saturn. The rings are beautiful now, and that present beauty is enough regardless of what the future may bring to the Saturn system. For most of the history of Saturn observation, scientists assumed the rings were ancient, dating back to the formation of Saturn itself, approximately 4.5 billion years ago. This assumption seemed reasonable because large-scale planetary features generally do date back to solar system formation, when planets coalesced from primordial materials. The rings appeared permanent and unchanging, suggesting a stability that implied great age rather than recent origin around Saturn. This assumption persisted for decades until new evidence began to challenge it seriously in recent years of observation. The first hints that the rings might be young came from observations of their color and brightness, compared to expectations for ancient material. Space is not empty, but contains a continuous rain of tiny dust particles, micrometeorites, and debris that accumulates on exposed surfaces, over time continuously. Objects that have been exposed to space for billions of years should show the effects of this bombardment, developing dark coatings from accumulated dust. The rings of Saturn are remarkably bright and clean, far brighter than expected if they had been exposed to billions of years of space dust. The brightness of the rings suggests they have not been accumulating dust for nearly as long as the solar system has existed. If the rings were 4 billion years old, they should be stained dark by accumulated contamination from meteoroid bombardment, continuing throughout that time. Instead, the ring particles appear fresh and relatively pristine, gleaming white when illuminated by sunlight from across the solar system. This pristine appearance is more consistent with a ring system perhaps 100 million years old rather than billions of years ancient. The mass of the rings also provides evidence for a relatively young origin when considered carefully against expected loss rates measured. The Cassini spacecraft measured the ring mass precisely during its final orbits between the rings and planet in 2017. The measured mass was lower than many models had predicted for ancient rings that had been slowly depleted over billions of years of existence. A lower mass suggests either that the rings started with less material or that they have not existed long enough to lose substantial mass yet. Combining the brightness and mass evidence, some scientists now estimate the rings may be only about 100 million years old maximum. This would mean the rings appeared roughly when dinosaurs were reaching their peak diversity on Earth during the Cretaceous period, long ago. The rings are not primordial remnants of solar system formation, but relatively recent additions to the Saturn system by this accounting. This young age, if correct, raises fascinating questions about how such a substantial ring system could have formed so recently in history. The formation of young rings requires a dramatic event capable of producing vast amounts of ice in orbit around Saturn, all at once. The most likely scenario involves a moon being torn apart by Saturn's gravity after wandering too close to the planet's tidal influence. Saturn's gravity would have shredded the unfortunate moon, spreading its ice and rock into the disk that would eventually settle into the ring system we observe today around the planet. This hypothetical moon would have been substantial, perhaps 200 to 400 kilometers across, similar in size to Saturn's moon Mimas today. Such a moon orbiting too close to Saturn would have crossed the Roche limit, the boundary within which tidal forces exceed the moon's self-gravity. Inside this boundary, the gravitational stress from Saturn's immense mass would have pulled the moon apart over time gradually. The ice and rock that once formed a coherent spherical body would have spread into a disk orbiting the planet. The Roche limit for Saturn lies at approximately 140,000 kilometers from the planet's center, roughly where the outer edge of the main rings now resides today. Inside this boundary, no large moon can hold itself together against the differential pull of Saturn's gravity from near side to far side. The coincidence between the Roche limit and the ring extent supports the idea that the rings formed from disrupted moon material settling there. Material inside this limit cannot coalesce into a moon. Material outside can, which explains why moons exist beyond the rings, but not within them. An alternative formation scenario involves a comet or other icy body from the outer solar system being captured and destroyed by Saturn. If such a body passed close enough to Saturn, tidal forces could have torn it apart just as effectively as they would a moon. The debris would have spread into a disk around the planet, eventually forming the ring system observed today, orbiting continuously. This scenario seems less likely than moon disruption, simply because capturing an object into a stable ring-forming trajectory is quite difficult gravitationally. Collisions between existing moons could also have produced ring material, though this seems insufficient to explain the entire ring system observed. Saturn's moons do occasionally collide or experience catastrophic impacts from comets and asteroids passing through the outer solar system periodically. Such events would produce debris, some of which might contribute to the rings over time as material spreads through orbital mechanics. However, a single massive disruption event better explains the relatively uniform composition and substantial mass of the main ring system. The composition of the rings provides some constraints on their origin, though not enough to identify the parent body definitively with certainty. The rings are approximately 95% water ice, with small amounts of rocky material and organic compounds mixed throughout the structure. This composition is consistent with a disrupted icy moon, which would have been mostly ice, with a small rocky core at center. A comet would also be mostly ice, making composition alone insufficient to distinguish between these formation scenarios conclusively. If the rings did form approximately 100 million years ago, we are observing them during a relatively brief window in Saturn's history overall. For most of its 4.5 billion year existence, Saturn may have been ringless, or may have worn different rings that formed and dissipated. The current rings are temporary, destined to disappear within the next 100 to 300 million years through ongoing loss processes operating. We happen to exist during the small fraction of Saturn's lifetime when these particular rings are present and visible. The timing seems remarkably coincidental, raising questions about whether we are simply lucky or whether something about this period favors ring formation. One possibility is that ring systems form and dissipate multiple times throughout a planet's history, making any given moment reasonably likely for observation. Another possibility is that conditions in the outer solar system have changed, making ring formation more or less likely at different epochs of history. Current evidence cannot distinguish between these possibilities, leaving the coincidence unexplained for now by researchers. The young rings hypothesis remains somewhat controversial, with some scientists arguing that recycling processes could keep ancient rings clean looking despite their age. Collisions between ring particles could expose fresh ice from their interiors, renewing the bright surfaces despite ongoing contamination from space dust. Material from Saturn's icy moons might continuously replenish the rings, replacing lost or darkened material with fresh, bright ice from distant sources. These processes could potentially maintain ring brightness even over billions of years if they operated efficiently enough throughout that time. The debate continues in the scientific community, with new observations and models being developed to test these competing hypotheses about ring age. Future missions to Saturn might help resolve the question by making more precise measurements of ring composition and mass loss rates occurring. For now, the evidence leans toward young rings, but the ancient ring hypothesis cannot be entirely ruled out by current data available. The rings remain somewhat mysterious in their origins, despite decades of intensive study by spacecraft and telescopes observing them. Whether ancient or young, the rings exist now, and their presence creates one of the solar system's most beautiful spectacles for observers. The origin matters scientifically, helping us understand how planetary systems evolve and change over time throughout their long histories. But the rings themselves are worth appreciating, regardless of when or how they formed in Saturn's distant or recent past around the planet. They orbit today, catching sunlight, slowly dissipating, following physics, beautiful in the present moment, regardless of their history. The particles that make up the rings are individually simple objects, chunks of ice orbiting a planet, nothing more than frozen water. Yet their collective behavior creates patterns, waves, and structures of stunning complexity visible from enormous distances across space. The origin of this complexity lies partly in the rings themselves and partly in the moons that share Saturn's system with the rings. These moons shape and sculpt the rings in ways that reveal the intricate gravitational dynamics at work throughout the system continuously. Saturn possesses more than 140 known moons, orbiting at various distances from the planet throughout its extensive satellite system. These moons range from tiny objects only a few kilometers across to Titan, a world larger than Mercury with a dense atmosphere. Each moon exerts gravitational influence on its surroundings, and for moons near the rings, this influence shapes ring structure directly and obviously. The relationship between moons and rings is intimate and ongoing, with both components of the system influencing each other continuously through gravity. The most dramatic moon-ring interactions occur where small moons orbit within or near the ring system itself, directly embedded in the ice. These shepherd moons, as they are called, confine ring material through their gravitational influence as they orbit alongside the particles nearby. Without shepherds, ring material would spread out over time, dissipating into ever thinner distributions across wider orbital ranges. Eventually, the shepherds act as gravitational barriers, pushing ring particles back toward the main ring body when they drift too close to the moon. Prometheus and Pandora provide the clearest example of shepherd moon behavior as they orbit near the narrow F-ring of Saturn. Prometheus orbits just inside the F-ring, while Pandora orbits just outside, together confining the ring material between them gravitationally. When ring particles drift inward toward Prometheus, the moon's gravity pushes them back outward toward the ring center efficiently. When particles drift outward toward Pandora, that moon's gravity returns them inward, keeping the F-ring narrow despite natural spreading tendencies. The F-ring itself shows remarkable structure created by these gravitational interactions, with its shepherd moons orbiting nearby continuously. The ring appears braided and kinked in high-resolution images, with strands that twist around each other in complex patterns visible from spacecraft. These features result from the gravitational perturbations caused by Prometheus as it passes the ring material on each orbit around Saturn. The patterns are constantly changing, with new features appearing and old ones dissipating as the moons continue their endless dance with the ring. Within the main A-ring, tiny moons, too small to see directly, create patterns that reveal their presence to careful observers studying the data. These moonlets carve propeller-shaped features in the surrounding ring material as they orbit through the dense particle environment around them. The leading and trailing wakes created by each moonlet's gravity spread outward, creating paired features visible in high-resolution images from spacecraft. Hundreds of these propeller features have been identified in the A-ring, each one marking an embedded moonlet only tens of meters across. The moon Pan orbits within the Anchor Gap, the prominent division in the outer A-ring visible in detailed images of the system. Pan is only about 28 kilometers across, tiny compared to the major moons, but significant for ring dynamics operating around it continuously. Its gravity keeps the Anchor Gap clear of particles, sweeping away any material that drifts into the gap from either side over time. Pan also creates visible waves in the gap edges, ripples that propagate outward from the moon's path through the nearby ring material. Similarly, Daphnis orbits within the Keeler gap, an even narrower division near the outer edge of the A-ring structure. Daphnis is only about 8 kilometers across, barely visible even to Cassini's cameras during close approaches to the ring system. Despite its small size, Daphnis maintains the Keeler gap through its gravitational influence on particles attempting to enter the cleared region. The gap edges show dramatic waves where Daphnis has recently passed. The ring material, disturbed by the tiny moon's gravity, pulling on nearby ice. The Cassini division, the most prominent gap in Saturn's rings visible from Earth through modest telescopes, is maintained differently from the smaller gaps. No moon orbits within the Cassini division, yet it remains relatively clear of particles compared to the dense B and A rings flanking it. The division is maintained by orbital resonance with the moon Mimas, which orbits far outside the ring system entirely at distance. Particles that wander into the Cassini division find themselves in orbits that are exactly half the period of Mimas's orbit around Saturn. This 2-to-1 resonance means that particles in the Cassini division receive a gravitational kick from Mimas at the same point in their orbit repeatedly. Over thousands of orbits, these repeated kicks add up, pushing particles out of the resonance region and into the adjacent rings instead. The process is slow but inexorable, clearing the Cassini division of most particles over time, despite continuous drift of new material into the region. Mimas sculpts the rings from a distance, never approaching them closely, yet shaping their most prominent feature constantly. Other moons create similar resonance effects throughout the ring system, though most are subtler than the Cassini division produced by Mimas. The moon Janus creates a sharp outer edge to the A-ring through a 7-to-6 resonance with particles at that location orbiting Saturn. Particles beyond this edge are pushed outward by Janus's influence, while particles inside it remain confined to the main ring structure there. The precise correspondence between predicted resonance locations and observed ring features confirms our understanding of these gravitational dynamics operating throughout the system. Beyond the main rings, Saturn's moons contribute material to fainter outer rings through various processes ongoing continuously in the system. The E-ring, a broad and extremely faint ring extending millions of kilometers from Saturn, is fed by the moon Enceladus orbiting within it. Enceladus has active geysers at its south pole that spray water ice into space continuously, providing fresh material to the E-ring always. Without this continuous supply, the E-ring would dissipate within decades, its particles spreading out until they became undetectable by instruments. The connection between Enceladus and the E-ring was confirmed by Cassini observations, showing that the ring is densest near the moon's orbital position. Moving away from Enceladus in either direction, the ring thins out as particles spread along the orbital path over time after ejection. The particles themselves are tiny, mostly less than a micrometer in size, visible only through their collective scattering of sunlight. These tiny grains are continuously lost and continuously replaced by Enceladus's geysers, maintaining the ring in a steady state balance. The relationship between moons and rings represents one of the most intricate examples of gravitational dynamics in the solar system today. Every significant structure in the rings can be traced to some gravitational influence, whether from embedded moons, resonances with distant moons, or interactions between particles themselves. The rings are not passive collections of debris, but active systems shaped by forces that continue to operate at every moment continuously. Understanding the moons helps us understand the rings, and studying the rings reveals the presence and influence of moons too small to see directly. This understanding comes primarily from one spacecraft that spent 13 years orbiting Saturn and studying its ring moon system in detail. The Cassini mission, which ended in 2017, transformed our knowledge of Saturn's rings more than any previous observation effort ever attempted. Its discoveries continue to reshape our understanding of the rings, even years after the spacecraft's deliberate destruction in Saturn's atmosphere. The mission deserves attention for what it revealed and how it changed our view of this remarkable planetary system forever. The Cassini spacecraft launched from Earth in October of 1997, beginning a journey that would take nearly 7 years to complete across the solar system. The spacecraft carried 12 scientific instruments designed to study Saturn, its rings, its moons, and its magnetic environment in unprecedented detail. Cassini also carried the Huygens probe, built by the European Space Agency to descend through the atmosphere of Titan and land on its surface. The mission represented an international collaboration involving thousands of scientists and engineers from 17 different countries, working together. The long journey to Saturn was not direct, but involved gravity assists from Venus, Earth, and Jupiter to gain the speed needed. Each planetary flyby bent Cassini's trajectory and added velocity, allowing the spacecraft to reach Saturn without carrying impossibly large amounts of fuel. The route covered 3.5 billion kilometers, a distance so vast that light itself takes more than an hour to traverse it. Cassini arrived at Saturn in July of 2004, entering orbit around the ringed planet after 7 years of patient travel. The first images returned from Saturn orbit exceeded all expectations for detail and beauty when they arrived on Earth through radio signals. The rings appeared in stunning clarity, revealing structures that ground-based telescopes could never resolve across the vast distance separating Earth and Saturn. New features appeared in nearly every image: waves, gaps, clumps, and patterns that spoke of complex dynamics operating throughout the ring system continuously. Scientists found themselves with more data than they could immediately process, a wealth of information about Saturn's rings and moons. Over 13 years of operations, Cassini completed 293 orbits of Saturn, each one designed to study specific aspects of the system. Some orbits passed close to particular moons, allowing detailed imaging and measurement of their surfaces and properties throughout the mission. Other orbits focused on the rings themselves, skimming close to the ring plane to observe structures from new angles never before achieved. The mission was repeatedly extended beyond its original 4-year plan, as new discoveries demanded further investigation and observation continued. The ring observations from Cassini revealed a level of complexity that no previous mission or observation had anticipated beforehand at all. The rings were not simple, uniform bands, but intricate structures with features at every scale from kilometers down to mere meters across. Waves propagated through the rings, caused by gravitational interactions with moons and by the ring's own collective gravity field, operating continuously. Clumps appeared and disappeared, moonlet's carved propeller shapes, and the overall structure evolved visibly during the mission's 13-year observation span. Cassini's instruments measured not just the appearance of the rings, but their composition, temperature, and physical properties in detail throughout. Infrared observations revealed temperature variations across the rings, with the dense B ring remaining cooler than the sparser A ring typically. Spectroscopic measurements confirmed that water ice dominates the ring composition, with small amounts of contaminants providing the subtle colorations visible in enhanced images. These measurements provided constraints on ring age and origin that continue to inform scientific debates about ring formation today. The discovery of ring rain came from Cassini's observations of Saturn's atmosphere and magnetic environment. During the orbital mission, instruments detected water molecules in Saturn's upper atmosphere at locations connected to the rings by magnetic field lines threading through space. This water could only have come from the rings, falling along magnetic field lines as charged particles spiraling down toward the planet. The rate of this rain, measured in thousands of kilograms per second, revealed that the rings are actively dissipating into Saturn constantly now. The mass of the rings was measured precisely during Cassini's final orbits, which passed through the gap between the rings and Saturn's atmosphere. By tracking tiny changes in Cassini's trajectory as it passed close to the rings, scientists could calculate the gravitational pull of the ring material directly. The measured mass was lower than some models had predicted, providing evidence that the rings might be younger than previously assumed by researchers. This measurement remains one of the most important scientific results from the entire Cassini mission's long operational period. Cassini's cameras captured images that have become iconic representations of Saturn and its ring system in popular culture and scientific literature alike. The view of Saturn backlit by the sun, with the rings glowing translucent and Earth visible as a tiny dot in the background, moved millions of viewers. Close-up images of ring particles, gap edges, moonlets, and wave patterns revealed a world of intricate beauty at every scale examined by the instruments. These images continue to inspire scientific research and public fascination with the Saturn system years after they were captured. The mission's final phase, called the Grand Finale, took Cassini to places no spacecraft had ever been around Saturn before. During 2017, 22 orbits passed between Saturn's atmosphere and the inner edge of the D-ring, a gap never before traversed by any probe. These orbits provided the closest ever views of Saturn's cloud tops and the inner ring regions during their brief passages through the gap. The Grand Finale also enabled the precise mass measurements that have informed our understanding of ring age and evolution significantly. The decision to end Cassini by plunging it into Saturn's atmosphere was made to protect the potentially habitable moons from contamination by spacecraft materials. Enceladus, with its subsurface ocean and active water geysers, might harbor conditions suitable for life beneath its icy surface today. If Cassini were left to drift after running out of fuel, it might eventually crash into Enceladus, potentially contaminating that pristine environment. The deliberate destruction ensured that no earthly microbes hitched a ride to a possibly habitable world in the Saturn system. On September the 15th, 2017, Cassini made its final plunge into Saturn's atmosphere at high velocity after its last orbit around the planet. The spacecraft transmitted data until the very last moments, when atmospheric friction tore it apart and heated the fragments to incandescence, vaporizing them. Cassini became a meteor in Saturn's sky, ending its 20-year mission in the atmosphere of the planet it had studied so thoroughly for so long. The spacecraft is gone, but its data continues to yield new insights as scientists analyze the wealth of observations it returned to Earth. The legacy of Cassini extends beyond its scientific discoveries to its influence on how we see Saturn and its rings today. Before Cassini, the rings were known to be complex, but the depth of that complexity was not yet appreciated by researchers fully. After Cassini, we understand the rings as dynamic, evolving, temporary structures shaped by forces that continue to operate at every moment around Saturn. This understanding changes how we view not just Saturn, but ring systems throughout the solar system and perhaps around other planets elsewhere. Saturn is not the only planet in our solar system that wears rings around its equator in orbital bands of material. Jupiter, Uranus, and Neptune all possess ring systems of their own, though none rival Saturn's brightness or extent anywhere close to matching it. Comparing these different ring systems helps scientists understand what makes Saturn's rings so exceptional among the giant planets observed. The comparison also reveals common features that illuminate how rings form, evolve, and eventually dissipate around all giant planets over time. Jupiter's rings were discovered in 1979 when the Voyager 1 spacecraft passed through the Jovian system and turned its cameras backward. The rings had never been detected from Earth because they are extremely faint, composed of microscopic dust rather than reflective ice particles. Jupiter's rings are so tenuous that they are visible primarily in forward scattered light, when the sun illuminates them from behind and observers view the scene. In direct sunlight, the rings are nearly invisible against the backdrop of space surrounding Jupiter in its orbit. The main ring of Jupiter is only about 30 kilometers thick and composed of particles smaller than smoke particles in Earth's atmosphere typically. These tiny dust grains are continuously knocked off Jupiter's small inner moons by micrometeorite impacts, occurring constantly over time. The particles drift inward toward Jupiter due to atmospheric drag and electromagnetic forces, eventually falling into the planet's atmosphere and being lost. The ring is continuously replenished by new impacts, maintaining a steady state where loss and gain roughly balance each other. The faintness of Jupiter's rings, compared to Saturn's, results primarily from their composition rather than their mass or extent alone specifically. Dust particles scatter light poorly compared to larger ice chunks because each particle has much less total surface area for reflection. Saturn's rings contain particles ranging from dust-sized to house-sized, with the larger particles providing the reflective surfaces that make the rings so bright. Jupiter's rings lack these larger particles, containing only the fine dust produced by continuous erosion of the small inner moons. The difference in composition likely reflects the different environments around each planet and their effects on ring material over time, continuously. Jupiter's intense radiation belts may prevent larger particles from surviving, breaking them down into dust through energetic bombardment processes. Jupiter's stronger gravity also pulls material inward more quickly, giving large particles less time to accumulate before being lost to the planet. Whatever the cause, Jupiter's rings remain a faint and ghostly presence compared to Saturn's brilliant bands, visible from vast distances. Uranus possesses a ring system discovered in 1977 through stellar occultation observations from Earth-based telescopes pointed at it carefully. When Uranus passed in front of a distant star, the star winked out briefly several times before and after the main planetary occultation event. These additional winks revealed narrow rings around Uranus, blocking the starlight as they passed between the star and Earth's observers watching. The discovery was accidental, but opened a new chapter in the study of planetary ring systems in our solar system. The rings of Uranus are dark, narrow bands composed of particles much less reflective than Saturn's bright ice chunks overall in comparison. The particles are charcoal black, likely coated with organic compounds, or darkened by radiation exposure over long periods of time accumulated. 13 distinct rings are known, most of them very narrow, ranging from a few kilometers to about 100 kilometers in width typically. The rings are confined by shepherd moons in some cases, similar to Saturn's F ring and its shepherds Prometheus and Pandora orbiting nearby. Neptune's rings were suspected from stellar occultation observations, but not confirmed until Voyager 2 flew past in 1989 directly. The rings are even fainter than those of Uranus, requiring the spacecraft's cameras to detect them during close approach to Neptune. The most unusual feature of Neptune's rings is the presence of arcs, regions where ring material clumps rather than spreading uniformly around the ring path. These arcs should disperse over time due to orbital mechanics, yet they persist, confined by resonances with the moon Galatea orbiting nearby. The arcs in Neptune's rings present a puzzle because they should spread out into uniform rings over relatively short timescales by gravitational effects. The resonance with Galatea explains their confinement to some extent, but the details remain not fully understood by researchers even today. The arcs may be temporary features, destined to dissipate eventually, and perhaps reform elsewhere in the ring system over time. Observing how the arcs change over decades may help scientists understand the forces that shape and confine ring material throughout planetary systems. Comparing the ring systems reveals that Saturn's rings are exceptional in both brightness and mass among the giant planets of our solar system. Saturn's rings contain more material than all other planetary rings combined by a substantial margin, without close comparison from the others. The reason for this difference is not entirely clear, though Saturn's location and history may play important roles in explaining the difference. Whatever the explanation, observers are fortunate that the most spectacular ring system happens to be visible through modest telescopes from Earth's surface. The brightness of Saturn's rings results from their composition of water ice particles that reflect sunlight efficiently across vast distances. Jupiter's dust rings, Uranus's dark rings, and Neptune's faint arcs all lack this reflective quality that Saturn possesses in abundance around it. If Saturn's rings were composed of the same dark material as Uranus's rings, they would be far less prominent visually, even with the same mass present. The ice composition that makes Saturn's rings temporary through ring rain and loss processes also makes them beautiful while they last for observation. The temporary nature of ring systems appears to be universal among the giant planets of our solar system orbiting the Sun. Jupiter's dust rings are continuously replenished and lost, maintaining a steady state rather than a permanent structure around the planet. Uranus and Neptune may have had more prominent rings in the past, now faded to their current faint remnants through ongoing loss processes. Saturn's rings, though currently spectacular, are following the same path toward eventual dissipation into the planet's atmosphere over geological time. The existence of rings around all 4 giant planets suggests that ring formation is a common occurrence in planetary systems throughout the cosmos. Any large planet could potentially capture or generate ring material through various processes occurring during its long orbital history around a star. The rings may come and go over the lifetime of a planet, forming from disrupted moons or captured comets and dissipating through loss processes afterwards. The solar system we observe today captures these ring systems at various stages of their own individual evolutionary cycles continuing. The comparison to exoplanets remains speculative because we have not yet confirmed rings around any planet outside our solar system definitively. Some observations hint at possible ring systems around distant giant planets, but none have been confirmed to the satisfaction of most astronomers yet. The detection is difficult because rings are faint compared to the planets they surround, and exoplanets themselves are challenging enough to observe directly. Future telescopes may reveal whether Saturn-like ring systems are common throughout the galaxy, or whether our Saturn is exceptional somehow. For now, Saturn remains the solar system's undisputed ring champion. Its brilliant bands, visible to anyone with a small telescope, and patience. The comparison to other planets highlights just how remarkable Saturn's rings are among all known planetary ring systems anywhere in space. Whether ancient or young, whether permanent or temporary, the rings are extraordinary features of our solar system's second largest planet, orbiting the Sun. Understanding their nature through comparison and observation enriches our appreciation of what exists right now in our cosmic neighborhood. The rings of Saturn exist tonight, at this very moment, orbiting the distant planet in darkness, lit only by faint sunlight reaching across the solar system. Particles of ice continue their endless orbits around Saturn, each one following the path gravity dictates at its particular distance from the planet. The gaps remain clear, maintained by moons and resonances that have operated for longer than any human record of observation exists today. Nothing visible has changed since the last clear night when someone pointed a telescope towards Saturn to observe its rings from Earth. The processes we have explored continue without pause or awareness of any observer watching from billions of kilometers away at Earth's orbit. Ring rain falls into Saturn's atmosphere at thousands of kilograms per second, a loss too slow to perceive, but inexorable over time nonetheless. Particles in the innermost rings spiral slowly inward, losing orbital energy to the faint drag of Saturn's upper atmosphere, reaching toward them constantly. The rings are a few micrograms lighter than they were when this sentence began, a change utterly unmeasurable, yet absolutely real in physics. The moons continue their orbits, Pan sweeping through the Encke Gap, Daphnis rippling the edges of the Keeler Gap as it passes nearby. Prometheus and Pandora shepherd the F-ring, their gravity confining the narrow band of particles between their orbital positions endlessly. Mimas, far outside the rings, continues to clear the Cassini division through the patient accumulation of gravitational kicks over countless orbits around Saturn. The dance of moons and rings proceeds exactly as it has for longer than human civilization has existed on Earth below. Saturn itself continues its slow orbit around the Sun, taking nearly 30 Earth years to complete one circuit of its path. The planet's tilt changes as it orbits, presenting different angles of its ring system to observers on Earth throughout the long Saturnian year. In 2025, the rings will appear edge-on from Earth's perspective, almost invisible as the thin ring plane aligns with our line of sight. Then they will open again over the following years, returning to the spectacular sight that has inspired wonder for centuries of observation. The disappearance in 2025 is temporary, a geometric effect rather than any actual change in the rings themselves around Saturn. The rings will still be there, still orbiting, still losing material to ring rain, and gravitational processes operating constantly in the system. Only our view will change, the angle of observation making the thin rings invisible until the geometry shifts again over following years. This periodic hiding and revealing has occurred throughout human observation of Saturn since Galileo first saw the rings in 1610. Galileo himself did not understand what he was seeing when he first observed Saturn through his primitive telescope that year long ago. He described the planet as having ears or handles, lumps on either side of the main disk that he could not resolve into their true form. Later observations, as his telescope improved, confused him further when the rings briefly disappeared during an edge-on presentation that occurred then. The rings remained mysterious until Christian Huygens correctly identified their nature as a thin, flat disk in 1655, decades later. Since Huygens, humans have watched Saturn's rings through ever-improving telescopes for nearly 4 centuries of continuous observation now. The rings have been there for every observation, appearing and disappearing as Saturn's tilt changed, but never actually changing in any detectable way. We know now that they are changing, that they are slowly dissipating, that they will eventually be gone entirely from around Saturn forever. But this knowledge comes from measurement and calculation, not from any visible difference a human observer could perceive watching Saturn directly. The rings tonight look exactly as they looked when Galileo first saw them, when Cassini discovered the division bearing his name, when Voyager first flew past. They will look the same tomorrow, next year, next century, and for many centuries to come, without any perceptible change visible to observers. The dissipation is real, but so slow that human timescales cannot encompass it through direct observation of the ring system itself. We know the rings are temporary only because we can measure their loss rate and extrapolate forward across millions of years mathematically. This combination of visible permanence and actual impermanence makes Saturn's rings a meditation on time and observation for those who consider them. What appears eternal is actually temporary. What seems unchanging is actually flowing away, moment by moment, continuously around the planet. The ice that orbits tonight will eventually fall into Saturn, replaced by new ice spiraling inward from farther out until that too is depleted. The process is too slow to see, too fast to allow the rings to last, measured in timescales that dwarf human experience, yet are brief by cosmic standards. 100 million years ago, the rings may not have existed, and Saturn may have appeared as a ringless sphere to any observer present. 100 million years from now, the rings may be gone or reduced to faint traces of their current glory visible only with sensitive instruments. The window during which the rings are prominent and visible is short compared to Saturn's lifetime orbiting the Sun in our solar system. We happen to exist during this window, able to see something that past and future beings may never witness firsthand. The coincidence of our existence with the ring's presence is either pure chance or indicates something deeper about ring system frequency in planetary evolution. If ring systems form and dissipate many times during a planet's history, then any given moment is likely to catch some rings somewhere. If Saturn's current rings are a unique or rare occurrence, then our timing is remarkably lucky for observation purposes at this moment. Current evidence cannot distinguish between these possibilities, leaving the coincidence unexplained, but worth noting and considering quietly. What remains certain is that the rings are present now, available for observation, beautiful against the darkness of the outer solar system. Anyone with a small telescope can see them on a clear night when Saturn is visible above the horizon in the sky. The view is modest compared to spacecraft images, but unmistakably Saturn, the ringed planet, unlike anything else in the sky visible from Earth. The rings catch sunlight and glow thin and bright, surrounding a world 10 times larger than Earth, far away. The distance between here and Saturn varies as both planets orbit the Sun at their different distances and speeds around it. At closest approach, Saturn is about 1.2 billion kilometers away, a distance light takes more than an hour to cross between worlds. At farthest, the distance exceeds 1.6 billion kilometers, making Saturn among the most distant objects visible to the naked eye in our skies. Across this immense gulf, the rings remain visible, testimony to their brightness and extent, despite the vast separation between observer and subject. The light from Saturn's rings tonight left the planet more than an hour ago, traveling at 300,000 kilometers per second toward Earth. What we see is Saturn as it was, not as it is at this moment, though the difference is too small to matter for any practical observation purpose. The rings we observe have already moved slightly in their orbits since the light began its journey toward our eyes and instruments. The universe delivers its information with inherent delays that we accept without usually noticing them, consciously during observation. The night continues. Saturn orbits, the rings orbit Saturn, and the particles orbit within the rings at their various distances from the planet. Nothing requires our observation to continue. Nothing depends on our awareness of what is happening far away in the outer solar system tonight. The processes we have explored proceed whether anyone watches or not, following physics, indifferent to meaning or appreciation from any observer. Saturn and its rings exist in their own right, not for us, though we are fortunate to be able to see them nonetheless. This exploration has traveled from the appearance of the rings to their composition, from their structure to their dynamics and their fate. We have followed the particles on their slow journey toward destruction, understood the moons that shape and sculpt the ring system constantly. We have honored the Cassini mission that revealed so much about what exists at Saturn in the outer solar system. We have placed Saturn's rings in context among the ring systems of other planets throughout the solar system for comparison. What remains is simply the rings themselves, existing as they do, orbiting as they must, dissipating as physics demands they shall. The beauty is present regardless of understanding. visible to any eye that turns towards Saturn on a clear night from Earth. The science enriches the viewing without replacing the simple wonder of seeing something so remarkable and beautiful through a telescope or in images. Saturn's rings are temporary, but they are present now. And now is when we are able to appreciate them directly. The ice continues to orbit, the gaps remain clear, the shepherd moons tend their flocks of particles in the darkness of space, far away. The ring rain falls silently into Saturn's atmosphere, invisible and continuous, without any pause or interruption occurring. The timeline stretches forward toward an inevitable conclusion that no living human will ever witness when the rings finally vanish entirely. For now, and for countless nows to come, the rings remain, patient and ongoing, following their orbits around the great ringed planet in our solar system. Saturn is there tonight, if the sky is clear and the hour is right for observation from wherever the listener rests on Earth. The rings are there, thin and bright, catching light from a sun nearly 1.5 billion kilometers away across the solar system. They are beautiful, they are temporary, they are present in this moment that will not come again in quite this way, ever, throughout cosmic time. The observation is available to anyone who chooses to make it, a simple gift from the universe requiring only a telescope and a clear sky tonight. And so the exploration rests, having covered what is known and what is beautiful about the rings of Saturn orbiting far away. The rings continue without regard for the exploration, following physics, slowly disappearing, but not yet gone from our view for now. The listener may rest with the knowledge gained, may look for Saturn in coming nights, may remember that something beautiful is slowly vanishing in the outer solar system, or may simply drift into sleep, knowing that the rings are there, that they are remarkable, and that understanding enriches but never replaces the simple wonder of their existence in space. Good night from the drowsy astronaut, and I hope see you again tomorrow.